Okay, so given some information, right, and not a specific function, the idea is we want to sketch f of x. So where are we going to start? What's the first thing we're going to do?
Plot the points that they give.
Yeah, plot the points they give us, right? So f of negative 2. So you can see we need some numbers, right? We need f, so we need the x values to be like 0 and 2 and negative 2. So we might want to just put a little scale down, 1, 2, and I've got to go to 6, at least 6, right? 2, 3, 4, 5, 6, 7, 8. Okay, so we'll label that 6 because I need to approach 6 from below. We need f of negative 2, so we get negative 1, negative 2. Okay, label that negative 2. And we'll give you a grid, right? I mean, it's just, just cut back, so we've had to go with no grid on this. F of 2 equals 4, so 1, 2, 3, 4, and negative 1, negative 2, whatever. All right, so let's plot some points. Okay, let's do the points in red. So f of negative 2 is equal to 1. Right, so we got a point there. F of 0 is negative 2. We got a point there. F of 2 is equal to 4. We got a point there. Okay, now what? All right, so f prime of 2 is undefined, but the function's continuous, so what's probably happening, we don't think we're going to sketch anything, but what's probably happening at f of, at 2?
Point of inflection.
Point of inflection, or, okay, so let's keep looking, and f prime of 0 is 0, so what's likely going on there? Given that these points are up here, probably got a minimum down here, right? Okay, so we got a minimum here, and we've got an undefined, now would a point of inflection be undefined? I think undefined is usually a corner, right? So there's a kink, or, okay, so we'll kind of keep that in mind. What does this say?
From negative 2 to 2, it's concave up.
Right, so we're going to draw this from negative 2, okay, so that kind of makes sense, right? This would be a minimum, so yeah, let's see, can we draw that in now? What else do we have? So limit as x approaches negative infinity of f of x equals 4. Okay, so that says we must have a horizontal asymptote, right?
Yeah.
Going that way. This is concave up. This is probably just going to kind of head off that way and be concave down, right? And as x approaches infinity is 4. Limit as x approaches 6 from below. Okay, so probably a horizontal asymptote there, right? Because we're going down to negative infinity. And from here, well, so we're not going to smooth, curve that. We're just going to kind of, right? So we'll throw a little corner up there. And, oh, I guess that's pretty much it, eh?
Wouldn't at negative 2 have to be a point of inflection?
Sure, kind of looks
Otherwise,
it too.
it wouldn't make sense for p prime of 2 or f prime of 2 to be undefined.
Yeah, so there's your point of inflection. Right? So
Oh, okay.
concave up, concave down. Change here.
Okay.
Yeah, POI. Yeah, because we know that's where it's going to change, right? But where else? Then there's a point, well, it's not really a point of inflection because it ends up being a, okay. Yeah. So there we go. And the idea then is just that you've done it in pencil and that you then go back through and just sort of make sure that everything kind of lines up and say, yeah, all right. I think it's good. Okay, so I'll just say this out loud because it's on here. So the steps are A through H are on page 233 of your book. And basically A, so find the domain. B, y-intercept, which is usually pretty easy to find, right? Because you're just setting x to 0. X-intercepts, yes and no. I mean, it depends. If it's really difficult to find them, then don't, I mean, they'll sort of come out eventually. Symmetry, right? So we're looking for even symmetry or odd symmetry. And there's one other type of symmetry we haven't discussed, but we will talk about in a bit. D, asymptotes, so look for vertical asymptotes, horizontal asymptotes. Domain is going to relate to that, right, as far as vertical asymptotes go. E, intervals of increase and decrease, so the whole first derivative test. F, local max and min points coming out of the first derivative test. G, intervals of concavity, so now we're doing the second derivative, and points of inflection, and H, sketch the function. But A through D, we can do a preliminary sketch, right? So if we have intercepts, we can sort of have a preliminary sketch going. So if we gave you this on a test and sort of a grid, you could be, as you do A, domain, well, you're not going to sketch anything, but as you do B and you find the intercepts, you can mark those in. As you find symmetry, you can just sort of keep that in mind. It's just a reflection in the y-axis, so really I'm just worried about graphing to the right, and then I'll just reflect it. Or it's odd symmetry, then I'm going to do a double reflection or rotation. Asymptotes, you can sketch those in, so sketch in the vertical and horizontal asymptotes as dashed lines. And you can do the little, okay, I know it's doing this here, right? Because if you do vertical asymptote, you're going to have to figure out where is it going, right? What's the behavior to the left of, and what's the behavior to the right of the vertical asymptote? So we need to know, are they both negative infinity? Is it one negative, one positive, and which one? Okay. So, and you can sort of sketch that. You put that on your preliminary sketch, right? So sketch in the asymptote and then do that. What else? That's pretty much it for a preliminary sketch, and then you've got your intervals of increase, decrease, and that comes into the final sketch. Once you've done E, F, and G, your intervals of increase and decrease, your concavity, then you can, and your min and max, so you can plot your min and max points and worry about how am I going to draw this, and is it concave up or concave down, increasing, decreasing. Right, and we kind of looked at that yesterday a little bit, right, with the concave up increasing and so on. All right, so let's do the first one. So f of x is equal to 4x squared over x squared plus 1. Now on your sheet, there's some useful information, which is just basically stuff you wouldn't know because you don't have a calculator, but you could figure out what we're giving you for E and F. So some of you probably have A, B, C, and some of you have D, E, F. For the, it's a half page, so it was redone. Anyway, doesn't matter. What do we do? 4x squared, f of x is, all right, so here's the deal. All right, domain. So what's the domain? All real numbers, right? I mean, what are you looking for in the domain? Are you saying, hey, can the denominator be 0? Nope. I'm wondering if maybe I'll draw that over there. And so for as we find stuff, we can sort of put it on the grid. Okay, what's next? Intercepts. B, intercepts. Okay, so y-intercept occurs when x is 0. When x is 0, what do we get? 0, right? So y-intercept, y-int means that x is 0, leads us to a 0, right? Because 4 times 0 squared is 0, and who cares? It's not 0 in the denominator. Y-intercept, so x-intercept, same deal, right? I mean, 0, 0 is the x and y-intercept. Are there any other x-intercepts? Let's say, no, there's no other way I can get that to be 0, right? Okay. Symmetry. What do we do for symmetry? So we want to work out f of negative x, right? Okay, so that's going to be 4 times negative x quantity squared over negative x quantity squared plus 1, which is 4x squared over x squared plus 1, which is the original function. So what does that tell us?
It has even symmetry.
It has even symmetry, and what does that mean?
It's symmetry about the y-axis.
Exactly. So even symmetry, right? And then we can say, so that means if I want to make a note of that, I'm going to reflect about y-axis. Reflect about y-axis. So that means that if we're drawing this, we really only need to worry about, hey, what's going on to the right? Okay? And then once we've sketched out the right-hand half of the graph, we can just reflect that. Okay, next, symmetry, asymptotes. Any vertical asymptotes?
No,
No. How do you know that?
you can't root -1.
Yeah, asymptotes. Well, I mean, so our domain would have told us if there's a vertical asymptote, right? Because your domain, so if your domain is real numbers, then, well, there's nowhere that it doesn't not exist, right? Okay, so vertical asymptote, none. Horizontal asymptote. So what are we looking for there, right? So horizontal asymptote, we're looking for the limit as, so remember vertical asymptote, we're looking for the limit as x approaches some number from the left and the right. Okay, so every vertical asymptote, you're looking at two limits, right? Approaching from the left, approaching from the right. If there's two vertical asymptotes, you're doing four limits. Okay, horizontal asymptote, limit as x approaches plus or minus infinity. Okay, and then we decide, do we have to, well, we shouldn't have to refine that, right? Because it's symmetrical, so it really shouldn't matter which way we go. Okay, it's just going to be a reflection anyway. So this really will be, plus or minus infinity can be the same value. Right? Of what? Of the 4x squared over x squared plus 1. And so that leads to the limit as x approaches plus or minus infinity of 4x squared over x squared over x squared over x squared plus 1 over x squared. Which, huh? Yeah.
Just said over x squared.
Whatever. What I wrote is what I should have said. I guess that's equal to, really, right? So that equals limit as x approaches plus or minus infinity of 4 over 1 plus 1 over x squared, which is 4. Smaller than 4? So are we coming at this from below or bigger than 4?
Tiny bit smaller.
Tiny bit smaller, right? Because we're not dividing by 1, we're dividing by a number that's a tiny bit bigger than 1. So we're going to end up with a number that's a tiny bit smaller than 4. Okay? So that equals 4. Right, and then we can just note here from below. I mean, at some point, it's just going to become obvious anyways, right? Like, I mean, when you go to sketch, oh yeah, okay, that's where it has to come from here. Okay, this is kind of nice. We sort of have an idea now, but you don't need that idea. What's next? Asymptotes. Intervals of increase, decrease. Okay, so what do we do for intervals of increase and decrease? Oh wait, so if we know we have a horizontal asymptote at 4, then we can sketch that in, right? Oh, dang, ran out of ink. Okay, you should be using pencil anyways. All right, we got a point, 0, 0, right? Okay. So this preliminary sketch, we can sketch this. If we had vertical asymptotes, we would draw in the vertical asymptotes, and we would, so if I knew, there's vertical asymptote there, and I knew that this was doing this, then I could sketch that in, right, in the preliminary sketch. You don't have to do it now, right? I mean, nobody knows how you drew this thing. I don't get a movie of you doing your thing, your stuff, right? I mean, it's just on a piece of paper, so it just happened. Okay, so what's next? E. Intervals of increase, decrease. Intervals. So what do we do? What do we got to do? Got to do the derivative. Okay. So do the derivative. I shall not make any comments about designated. I'll stop now. It's got to be a quotient, doesn't it? Oh.
4x.
Yeah. Just totally messed that up. Start over. What was it? X. 8x, right? Minus 4x squared times 2x. You know what I wrote first. If there's any resemblance to this. No, it's just 8x. Minus okay, that might be it. Is that it? Good. Verification. Anybody else? Is this the first derivative? Yeah? All right. Got a couple of people agreeing. We can't all be wrong. All right, so what do we do with this? We need the critical numbers, right? So critical numbers are where f prime of x is either 0 or undefined. It's not undefined, right? I mean, it can't be undefined. So then where is it 0?
0.
Okay, so what should we say here? Critical numbers, I guess, right? Critical numbers. So f prime of x exists everywhere. And f prime of x equals 0 when x equals 0. Okay, so that means what's happening there? So now we need to make our little chart, right? So let's chart it like. We got 0 sitting here. And what are our factors? So we've got 8, if you like, and x squared plus 1 squared, which will then tell us about f prime of x, which will say something about f of x. Okay, so how we go when we fill this in? Plus, plus, minus, plus, plus, plus. So let's say something. So we'll enumerate, I think that's the word though, we'll write it down. So we'll write down what are our intervals of increase and decrease. I mean, we can see them there, but let's make it explicit. So it's decreasing from negative infinity to 0, and it's increasing from 0 to infinity. Okay, so that's E. So I'm just going to go over here, and we'll do F. So what's F? What is, gave away my last one. I can do this from memory. Local max and min, right? Okay, so local maximum and local minimum. So what have we got? I mean, we know what we have. Okay. There is a local minimum at x equals 0. And then, so the point is 0, 0, right? So we already worked out that there is a point at 0, 0, so we knew that, or you substitute it back into the original and say, right, because, you know, we want to know what the coordinates are of that local minimum. Okay, and what's next? Concavity. I'm going to have to extend this page, I think. So concavity and points of inflection. Okay, what do we have to do for concavity and points of inflection? Yes, pause the video, right? It's just going to be... Then if I...
Well, yeah.
Well, the murder first, I think, and now it's recording, so the murder first. Okay, so second derivative, yes? Okay, so what do we have to do for the second derivative? We're going to find the intervals, increase and decrease, right? Because we're looking for concave up, concave down. And where would those appear?
3 to the power of -1.
1 minus 3x squared will be equal to 0. So 1 will equal 3x squared. So x squared is 1/3. So what's x?
Plus or minus 1/3.
Yeah. Plus or minus 1 over root 3. Okay, so then we can make a little table. And we've got negative 1 over root 3. We've got positive 1 over root 3. Or if you like, root 3 over 3. It doesn't really matter. And we've got an 8. And we've got a 1 minus 3x squared. And we've got something that's always positive. And that will tell us what the sign of, we still on F double prime. Extend the page again. Which then provides us information on f of x. Okay, 1 minus 3x squared, what sign?
Negative.
And then? And then?
Negative.
Yeah. Okay, basically anything big, right, so like 10, then this is going to be negative, right? It's going to be 100, 1 minus 300 will be negative. And anything small, well, it's being squared, so same deal. But stuff in here, like 0, you're just going to get 1 minus a small number, which will be positive. Okay, so negative, positive, negative, CD, CU, CD. So f of x is concave up on negative infinity and 1 over root 3 to, oh wait, no, it's the other way around. Concave up on negative 1 over root 3 to 1 over root 3 and concave down negative infinity to negative 1 over root 3 and 1 over root 3 to infinity. And that's a u in between there. Which,
You better believe that.
yeah, you better take it on faith, because I can't go in and clean that up without having to. And so what's happening at negative 1 over root 3 and 1 over root 3?
The point of inflection.
Point of inflection.
So it doesn't.
Okay, so we've got concavity. This is a bit of a mess here. So points of inflection, where there is a change in concavity, which is at, so x is equal to plus or minus 1 over root 3. So we need to stick those in and figure out what f of x is, right?
What's simplify mean?
I think classifying symptoms is what I came up with. Took a while. I'm going to submit it to Urban Dictionary. We'll see if it flies. Well, whether it's plus or minus root 1 over root 3 won't matter terribly, right? Because they'll both be positive. So f of 1 over root 3 is 4 times 1 over root 3 squared over 1 over root 3 squared plus 1. Okay, so f of negative 1 over root 3, well, first of all, we know it's symmetrical, and you're going to just square, so it's going to be the exact same number, right? So what is we got? What is we got? We got 4 over 3, and we've got 1/3. 4 over 3.
Yeah.
Or do I have something different? Yeah, something that's weird. Because I messed up, that's why. Okay, so what is that? 1. Okay, so POI. 1 over root 3, comma 1, and negative 1. All right, we have it all. So we have, so what's 1 over root 3? Root 3 is a little bit less than 2, so it's going to be like less than a half-ish. I mean, I guess we just write this in as 1 over root 3.
A bit more than a half.
A bit more than a half?
Less than a.
Oh, right, yeah, it's 1 over like 1.7 or something like that. Okay, and we've got a 1.
Quick response.
Okay, point of inflection, minimum value, concave, so what was it?
Up in that little portion.
Concave up in that little portion. So, up, down. Up, it refuses to sketch it properly. Up, wow, that's weird, I can't do this. Okay. I couldn't, I stuck a key.
It's concave.
Yeah, do you want to redo that?
Can I have a redo? I can do this. Okay, what is it? It's called, oh, it's concave up. Wow. That was weird. The hand wouldn't sketch the left side. So 4x squared over x squared plus 1. Y equals 4x squared over, and there we go. So what's 1 over root 3?
It does probably just have a weird, like,
It's scale. It's an issue of scale. So
See, my hero.
there. Yeah, mine's a little flatter down here than it should be, I guess. But it's your scale. It's to scale. This is to scale. This is working for scale. Okay, there we go. We've done one. Let's do another one. This one's a little tricky.
Oh my god, why? Why?
They don't pay us enough, so you know you gotta somehow.
Oh.
All right, yeah, we're not gonna be done by 11:30, just so you know, but you know it'll all be up here. It's okay because you can watch it with the sound off, right? And just say, yeah, I don't need to listen to this. Or actually, if I always play them back at double speed, but YouTube doesn't adjust the pitch. You know, like if you listen to iTunes or podcast or something, you play it at double speed, it takes the pitch down so it doesn't chipmunk, right? Because if you play normal voice fast, it's going to raise the pitch, right? And so iTunes adjusts for that. YouTube not as well, so it's a little pitchy. Yeah. Yeah. Oh my God. All right. Okay, so we are given a domain upon which to graph this, right? So we're told to graph this in 0 to 2 pi. However, oh no. However, well, we'll talk about this under symmetry, so that's C. A. What's the domain? 0 to 2 pi. Okay, so we're given a domain. B, the intercepts. What's y-intercept? Oh, sorry. Let me write down intercepts. So y-intercept, we set x equal to 0. Gives us the sine of 0 plus 2 cos 0, which is 2. So we got a y-intercept at 0, 2. X-intercept. We set y to 0. So at this point you ask yourself, can I do that? And you say, if I change sine 2x to 2 sine x cos x and factor out whatever, then yeah, we can work out the zeros, right? So this is 2 sine x cos x plus 2 cos x. So we can take out a 2 cos x and give us sine x plus 1. So we can solve them, and it's not a horrendous amount of work, right? So there may be ones you do where it's just like, yeah, you know, or maybe on this one you just say, yeah, I don't know. Okay, and you can worry about it later then. Because later on you're going to see approximately where they are. So at that point you might go, oh, wait a sec, yeah, I could work these out, right? Because they're going to obviously fall here. Okay, so 2 cos x equals 0 means x is equal to what? So it's where cos x is 0, which is pi over 2, 3 pi over 2, right? And sine x plus 1 means that sine x is equal to negative 1, which is also 3 pi over 2, so we don't need to repeat that. So we have pi over 2, 0, and 3 pi over 2, 0. So at this point, we may want to start our sketch. Okay, so I know, so let's go pi over 2, pi, 3 pi over 2, 2 pi. Preliminary, what do we have? 0, 2. And we had pi over 2, 0. And 3 pi over 2, 0. Okay, so we can sort of see, well, probably you're coming down from here, you're likely going to go negative at some point and then come back up maybe. Yeah, 0 to 2 pi. Okay, everybody good? Intercepts? So what's next? Symmetry. So this, I mean, we're only going from 0 to 2 pi, so we're not really going to worry about symmetry, right? Wait, you know, hey, it's symmetry, yeah, it's, you know. So it reflects about the y-axis, maybe, but I'm not really worried about that because we don't have to draw over there. But if we have a function of the form, so we could have symmetry of this form, right? If f of x plus 2 pi is equal to f of x, then we have what's called periodic symmetry, right? In other words, and this is likely periodic symmetry, right? Not so much when you look here, but when you look here and say it's 2 sine x cos x plus cos 2 or plus cos x, right? The period of all of these is 2 pi. So this has likely 2 pi symmetry. Well, it doesn't likely, it has symmetry every 2 pi. So if we wanted to sketch beyond 2 pi, we would just start repeating. Okay, and then we would just keep going. So we would call that periodic symmetry, right? Now you're going to find that in trig functions. Okay, so periodic symmetry, you know, is true for this function, which is actually g of x, right?
So do we need to know the like x plus 2h for symmetry for these?
Not for this particular one, but when you do other trig functions,
Okay.
you might just be on the real number line, right?
Yeah.
And you're just going to say, oh, hey, this has
So will we need to know it for this test here?
Yes.
Okay.
Having said that, I've covered my base. Is true for this function. So we could just draw 0 to 2 pi and then repeat. And then just translate the graph. Left and right. Okay, because whatever's happening in 0 to 2 pi is happening in 2 pi to 4 pi, and 4 pi to 6 pi, and 0 to negative 2 pi, and so on. Okay. Doesn't matter here. Asymptotes. What do you say about a trig function like that? There are no asymptotes. None. Right? It can't be vertical asymptote. It's defined for all x, and there's no horizontal asymptote. It's just a repeating, I mean, how high if you can't get to infinity? Sine x, cos x could be 1 times 1 or 1 times negative 1 or any numbers in between. Intervals of increase and decrease. What are we going to do? I'm going all over the place here. Let's do it here. So every time I write one of these out, I actually write out what it is, right? So A, domain, blah, B, intercept, blah. And if you do that, then you should eventually sort of know what all the steps are. So intervals of increase, decrease. What do we need? We actually did this one, didn't we? This function, we did this function the other day for some reason. I can't remember where, but I'm pretty sure we did this one. Yeah, I think it was in second derivative. We were looking at pi over 6. I think we were trying to say there was a local max at pi over 6 or something, or a local min at pi over 6. Okay, which means we should have a relatively smooth time doing the derivatives. Yeah, minus 2 sine x. Although actually now we're going to want to do something a little different. So the other day we did do this, but I think we were just showing that it had a local min or max at pi over 6, which meant we could just go straight to the second derivative, throw in a pi over 6, be positive or negative, therefore it's concave whatever, which leads to whatever. This time we actually need the critical numbers for this, right? So we're going to want to get rid of that cos 2x. So what could we replace it with? Thank God for formula sheets. There's a whole pot. I go with the 1 minus sine squared because then we have an expression simply in sine. And we'll have a sine squared, and we'll have a sine, and we'll have a number, and that may factor, right? So we're going to look for, okay. So what is it, 1 minus sine squared x? 1 minus 2 sine squared x?
Yeah.
Thank God for formula sheets. Okay, so what's that give us? 2 minus 4 sine squared x minus 2 sine x. So let's take a negative 2 out and rearrange. So I get 2 sine squared x plus sine x minus 1. Extend the page. So negative 2. Now that negative 2 is important, right? Like when we go to look at the sign of the first derivative, that's important because, and if you just drop that, because the zeros aren't important. The negative 2 doesn't matter for finding zeros, right? But it does matter because you'll flip everything around. It'll all be upside down. Okay, so this has got to factor. Plus, minus? Yes. Okay. And if it's no, let me know, right? As soon as possible. I don't want to know 3 pages later. Oh, hey, that was a... Okay, so we want, so g prime of x exists everywhere. And g prime of x equals 0 means that 2 sine x minus 1 is equal to 0. So sine x is a half, and so remember, we're just doing 0 to 2 pi. And even if we were graphing this beyond, we still just need to do 0 to 2 pi. Okay, so you're not sitting here going pi over 6 plus 2n pi, and you just say, hey, we're just going to worry about this one interval, and we know it's periodic. And what else do we get? Okay, so 3 critical numbers. So next step, chart. Page shall be extended. Okay, so we got 0, that's a boundary there. Pi over 6, that's 9 pi over 6. Okay, so 5 pi over 6. 3 pi over 2, and it ends at 2 pi. Okay, so we really have a bounded interval, right? We don't need to worry about below. We're not looking at everything below pi over 6. We're saying between 0 and pi over 6, between here, here, and here. And what were our factors? What's the most important factor? Not the most important. The negative 2 is an important factor, right? Which just makes everything negative. And then we have a 2 sine x minus 1. And then we have a sine x plus 1. Which gives us the sine of g prime of x, which gives us information on g of x, which we will then write out, right, as to our intervals of increase and decrease. I'm doing part of it. So sine x plus 1, well, the lowest it could go is negative 1. So now you're done, or you got a question? Okay, so fill in the chart.
The other two, but
Yeah.
follow the pattern.
Okay, so what are our signs on 2 sine x? Well, so sine x would be bigger than a half between pi over 6 and 5 pi over 6, right?
Correct.
So that would make this positive here,
Yes.
and then negative, and then negative, and then negative again,
Yes.
and then negative. Yeah, okay. So oh, okay. Oh, and so 3 pi over 2. What's going on there? Point of inflection. Okay, so what do we got? Increase, decrease, increase, increase. All right, so we should say that. We have g of x increasing from 0 to pi over 6 and 5 pi over 6. 5 pi over 6 to where? To 2 pi, right? since it is a point, we know this is going to be a point of inflection, right? Because it's continuous. If it was not continuous at that point, then I would have to split the interval, right? So maybe this is it's a hole or something. Then I would say 5 pi over 6 to 3 pi over 2 and 3 pi over 2 since the graph is, but it is continuous, so to 2 pi. Okay, so just make sure you know what's happening there, right? I mean, you could change, concavity could be changing there, which we think it is, right? Now we'll get the second derivative test, which will tell us, yeah, concavity is changing there. But concavity can also change based on, vertical asymptote or break a hole in the graph, something like that. So, and g of x is decreasing on pi over 6 to 5 pi over 6. Okay, so we can't sketch anything else yet. Okay, we got 3 points. Okay, so, then what? Local max or min, right? So what have we got going on? There is a
There's a local maximum at pi over 6 and a local minimum at 5 pi over 6.
Okay, so local maximum at x equals pi over 6. So now we got to figure out what are the actual coordinates, right? Now, does that, somewhere on this sheet, it gives us useful information. Is this part of the useful information? No? Okay. Did it give up? Did it tell us here? What? So sine x is negative a quarter. I guess that's coming in a bit later. Okay. So, so we can work that out though, right? So g of pi over 6 is equal to the sine of, okay if I just write pi over 3 in here? Yeah. Okay. Pi over 3 plus 2 cos pi over 6. So, okay, pi over 3 is what? That's root 3 over 2? Yeah. Root 3 over 2 plus cos pi over 6, so plus 2 root 3 over 2, right? Now, I think I'd rather leave it like that because the whole thing's going to be 3 root 3 over 2, right? As opposed to just saying, oh, this is 2 times root 3 over 2, which is root 3. It's more useful if it's over 2. So 3 root 3 over 2. So it gives us the point pi over 6, 3 root 3 over 2. And we have a local minimum, was it, at 5 pi over 6? So g, excuse me, at 5 pi over 6 is the sine of 5 pi over 3 plus 2 cos 5 pi over 6. Okay, so 5 pi over 3 is the same as pi over 3, right? But it's negative. And 5 pi over 6 is the same as pi over 6, but it's in quadrant 2, so it too is negative. It's negative. So that's negative 3 root 3 over 2, and it gives us the point okay. So at this point, I might want to sketch those in. What's 3 root 3 over 2? So root 3 is, well, about 1.7 something, 5.4, 2.7. Yeah, over 2, pi over 6, right? Where's that? How many 6s is that? It's like 3, right? So there's pi over 6 and some number up here, right? Which is what? 3 root 3 over 2. And 5 pi over 6, just going to be just shy. And negative 3 root 3 over 2. Okay, so there's a couple more points. What was that, F? So G is concavity and points of inflection. to disappoint you. It looks like we're going to have to continue tomorrow. Not that we'll finish this, but we're not going to get through the third one today. Okay, so what do we need? We need the double prime. Okay, so choice is, right, let's go from this, because that's going to be easier to work. You don't want to necessarily go from this, or this, or this. I guess you could go from this, but I'm not going to. So 2 cos 2x is 2 minus... do you want a lot of detail in this, or you don't really care? It's just sort of... Let's do it this way. So 2, and then we've got minus sine 2x. And then we got another 2 minus 2 cos x. So minus 4 sine 2x minus 2 cos x. So to be useful, we're going to replace the sine 2x with 2 sine x cos x, right? Because we need to do something with it, right? We need to find where this is 0. So minus 4 times 2 sine x cos x minus 2 cos x minus 8. Oh, factor it. What do we got? So we got a minus, oh, let's write it out. Minus 8. Okay, so negative 2 cos x, 4 sine x minus 1 plus 1. Ah, I think I see where this sine x of negative a quarter or sine of negative a quarter came from in the useful information, right? Okay, so step 1, verify, is this in fact true?
Sure.
Yeah, I like that.
Let's go.
You screwed up, but we're going to go with it anyway.
I'll tell you after class.
Yeah. Okay. It's what I have written on paper, so I have done this once before. But I had other errors before anyway, so. Okay, so g double prime of x exists everywhere. And g double prime of x equals 0 means that cos x equals 0. So x is pi over 2 and 3 pi over 2. Yeah, we already got those points, right? Pi over 2 and 3 pi over 2. So it'll be interesting to see, well, what are they? Well, that's when it's 0, so those are probably points of inflection. Not a guarantee, right? We need to check the intervals. And then what else? We got 4 sine x plus 1 equals 0, so sine x is equal to negative 1/4. Ah, that's where the useful information comes in, right? Because there's no way we know what the sine, what value of x gives us negative 1/4. Okay, so what values of x do give us negative 1/4? So x is equal to 3.394. And x is equal to 6.031. So now, we want to examine 0. That's bigger than pi, right? So pi over 2, 3.394, 3 pi over 2, 6.031, and 2 pi. And we are looking at this guy, which gives us what? Negative 2, so negative 2 and a cos x, and a 4 sine x plus 1. Taken together will give us the sine of the second derivative, which will tell us information about the curve. So the concavity and points of inflection. Cosine. Cosine is positive from 0 to pi over 2. And from 3 pi over 2 to 2 pi, right? And it's negative elsewhere, right? 2 pi over 2 and 3 pi over 2 will be negative. 4 sine x plus 1, so sine x. All right, so we know that the 3.394 and the 6.031 are sort of the what's going on points. So I know that sine is positive from 0 to pi, right? So from here to here, and that goes a little beyond pi, but I just need sine to be bigger than negative a quarter. So. And then sine's going to go negative after that, so then, and this is, so that'll be negative. And will it come back positive again? So.
Yeah, after like the 6.03.
Right, after this, because that's the dividing point, right? That's where it is negative. So above that, then it's going to be negative, but then it's multiplied by 4 and then 1 half. But it's smaller than negative a quarter, so the 4 times, then you add 1, you get a number that's positive. Yeah. That works. Okay, what do we got? Minus, plus, minus, plus, plus. Minus, right, yeah, sorry. Dang, never change.
Can you make like the ratio smaller?
Well, if I had written a minus incorrectly, it very easily changes to a plus. Yeah, you can. I'd have to adjust it though. Like I can't with my hand. It just when I do this, it's a constant size, right? It doesn't matter how big I spread my finger. It's just as long as there's multiple points of contact, then it knows it's an eraser. Okay, so what's happening?
Could you make an eraser with 2 pens?
Probably, yeah. Multiple points of contact. No. 3 pens.
You're welcome. People trying to learn later.
Yeah, no, I can't. Apparently, I'm not
Can
capable.
you make them with your fingers really far apart?
Can I do it? I don't even, well, 3 fingers won't. It's obviously late in the class, yeah. Okay. Concave up, yeah. Let's finish this. Concave down, concave up, concave down. So if you're changing from, yes. Yes, if you're changing from down to up or up to down, what's happening? POI. POI. Okay, so we got 4 poise. So did they give us a value for the original function at 3.394 and 6.031? Yes? No? What? What is that value?
G of 3.394 is about -1.45.
Okay, so let's go negative 1.45, and then I think it's just 1.45?
Yeah.
Okay, so at the 3 point, so where does that 3.031 come in? Oh, sorry, 3.394, between pi over 2 and 3 pi over 2. So it's bigger than pi, right? So that'll be...
Slightly bigger than pi.
Okay, so at 3.394, which is it, plus or minus?
Oh yeah.
So plus or minus 1.45. Negative? Okay, and then it's 6 point whatever is going to be here, right? So okay, this is 3.394, and this is 6.031, so it must be the positive one. Okay, so we got that point inflection, that point inflection, that point inflection, that point inflection. So I think we have all the points of inflection on here now, right? Okay. So g of x is concave up on the interval pi over 2 to 3.394 and 3 pi over 2 to 6.031, and it's concave down on 0 to pi over 2 and 3.394 to where? 3 pi over 2 and 6.031 to 2 pi. All right, so hopefully this is all on one piece of paper you can look at and then sort of, because, yeah, and I've just got it all over here. So it was, all right, so I've got it written down here. So it's concave down on the first interval from 0 to pi over 2, right? And it has a maximum at pi over 6. So it's going to climb up to the pi over 6 and then come down. So that's still going to be concave down. Okay, so it's going to do this and this. Okay, now concavity is going to change as it goes to the minimum. So it'll be concave up here
Still
to.
concave up until that point at 3.4 some.
So then here, now we've gone to concave down. Now we're still increasing here, right?
Yeah.
Because we're doing interval, so the interval, it's an interval of increase, right? So 0 to pi over 6 is increase, right? And 5 pi over 6, and then pi over 6 to 5. So going through 3 pi over 2, which is a point of inflection, right? Now, I never actually wrote the points of inflection, but there's one at 3 pi over 2, and there's one at 6.031.
Wait, shouldn't the 6.031 be negative because you get it by putting in an x value of -1/4? Wait. No, I'm dumb and wrong. I'm a failure. I'm a monster.
No, but so now I need to change. So we're concave
Then it's
down
just,
but increasing, and then we're concave up but still increasing,
and then it's concave
and
down
then it's
again, but
concave
still
down.
It's
and-
still increasing.
Yeah, and it's got to end up at 2, right? Because that's 2 pi away from there, so it should end up at 2.
Probably, but that's not our problem.
No, because we just need to end there. The elevator, not the bell.
Close enough.
Okay, so let's graph it and see. That's not the right thing. Why does it never switch? Okay, what were we looking for? Sine 2x plus 2 cos x.
Holy automobile.
Oh, he does.
Okay, let's take a look. So we wanted, so let's go a little below 0. It's like negative. And let's go a little above 2 pi. So 2 pi is 12, let's say 13. And let's step by, say, pi divided by 6. Okay, and I think the y-axis looks decent enough. Okay, so we have a maximum here at pi over 6. We've got the point 0, 2. Point of inflection, minimum, x-intercept. They've all left, but it's all there. Okay, so tomorrow, sketching, curve sketching, part 2.